If this definition is confusing, I'll put it up for a minute for you to stare in a second. Again, look at this picture. And a connected component basically corresponds to some sub-network here, a part of this network where everyone is connected to everyone. So notice that this dashed line didn't cut any links. And within the dashed lines, everyone is connected to everyone through some path. Okay? This is a component. So let me let you stare at that for a few seconds. Does this make sense? Okay. All right, so now let's think about the size of the largest component, which is what we are really interested in. So suppose that P is greater than 1 over n. So this essentially means that the average degree is greater than 1. Right? Because the average degree of any individual is greater than 1, because P times n is greater than 1. Okay? If the average degree is less than 1, this would suggest that we have a lot of isolated individuals. So kind of intuitively, this would mean that the large component would not be very large, but we'll get to that. Now let's denote by Q the fraction of nodes in the largest component. Now contemplate adding a node when the network is very large. So now I'm going to do a hand-waving exercise to just illustrate to you the size of the largest components. If this added node is of degree d, what's the chance it's outside of the large component, which has q nodes in it? It's the probability that none of the links is connected to the large component, right? So it means that each of the d links that come out of this node is not connected to the large component. So this is just the probability 1 minus q. So the probability that it's not in the large component is just 1 minus q to the power of d. So overall, now if we have a degree distribution which is p of d, the probability of not being in the large component is just the probability that you're of degree d and not in the large component, summed up over all the degrees. Okay? So we're just contemplating one individual and seeing what's the probability that are not in the large component. Well, it depends on their degree. The probability of being of each degree is P of d, and the probability conditional on that of not being in the large component is this 1 minus q to the b. Okay? So now let's plug the Poisson network into P of d, and to the summation, I'll save you the algebra. But if you stick the P of d that we've developed from before, this thing with the exponent, then what we get is a fixed point formula here. What we get is a formula that equates q with something that depends on q as well. This is unfortunately not something that's easy to solve, but it's a formula. Now q equals to 0 is always a solution of this. So notice that if I plug 0 here, this is 1. So the right-hand side is 0 and the left-hand side is 0. So this is all. But when the average degree is greater than 1, which is sort of this assumption that I started out with, there's a positive solution as well to this formula, as it turns out. Okay? And the way to see this is just by looking at essentially the intermediate value theorem. So you can just plug in q equals to 0 and q equals to 1 and see that the inequalities reverse when this thing equals to 1. So again, we face what I called before a phase transition. So we have this threshold function p that, and I say function because it depends on n, that determines whether you have a substantial large component, whether you have a large component that has a positive fraction q of nodes in it, or not. Okay? And this threshold function really is going to correspond to whether the average degree is greater than 1 or less than 1, which is sort of intuitive, I think. So basically, if you're likely to have isolated nodes, you're not going to have a very large component. Does this make sense? Formulas. Okay. So let's go back to the Reed-Frost model. So again, what we did is we took the network, we took out these immunized nodes. There are sort of fake nodes here. And then we looked for the large component. That's what's going to determine whether an epidemic is going to explode or not. So there are 1 minus pi times n relevant nodes. Recall that pi is the probability of being immunized. So if p times 1 minus pi n is less than 1, there is no giant component, and a small fraction of infected individuals will die out. This just corresponds to the average degree being less than 1. P times the effective number of nodes is greater than 1, so the average degree in our effective network is greater than 1. A small infection may spread out to the giant component, and in fact, we even have an equation for the size of this large component. We can even estimate for how many people it will spread out, because we have this equation. Now this is, like I said, not a great equation, but we can still draw a picture. And it basically looks as follows. So if we draw the picture as the size of the large component as a function of p times 1 minus pi times n, what we get is sort of this increasing curve. Okay? Which sort of makes sense. So the curvature for now is not very meaningful for us, but the fact that it's increasing sort of makes sense. Kind of the greater the number of nodes, the lower the number of immunized people, the greater the density of the network, the more linked individuals are, the larger the spread will be. So this sort of makes sense. Is this to me? But maybe to you now. Okay. But what's missing in these models is that there are no strategies, there are no dynamics. It's kind of a very simplistic take of networks. And this is where I'm going to go next. We're going to add basically these two elements. So the type of questions generally that we want to ask, so I want to step back and kind of re-ask the questions, are the following. So first of all, how do choices, and now I'm going to think about them as strategic choices, to invest in education, learn a language, and so on, depend on social network structure and the location within the network. And in particular, we'll want to know how does the network structure impact behavior and welfare, and the complexity of calculating equilibria in these networks, which I'll soon talk about. And we'll also want to know how relative location in a network impacts behavior and welfare. So these are the types of questions that I'll start out with. And this will be highly linked to how the behavior propagates through the network, which, like we said, is important for marketing, epidemiology, and so on. Okay, so let's start with an example, just to give you a sense of how these strategic forces may play roles. So let's think about a simple, what we call a public good game. And this is a situation where you gain 1 if anyone experiments, 0 otherwise, but experimentation is costly. So you can think about the example of hybrid corn. It might be costly to try out a new grain because it involves risk, but you'd like someone in your neighborhood to actually experiment. So if you were by yourself, let's assume that the costs are not so high that you would still prefer to experiment yourself. Okay? But you definitely prefer your neighbor to experiment and you to see the outcome of that. Okay, so this is really a simple game, 2 actions. So let's think about experimentation as the action 1 and no experimentation as the action 0. And let's think of a situation where everyone knows the network, and the network is very simple. It's what we call the star network. So we have 1 node that's connected to a bunch of other nodes that are not really connected to one another. Okay, so it's sort of like having a boss, like a reel, and we're all somehow connected to a reel. We're just starting to get to know each other. So this is one equilibrium of this network, where the central node chooses 0, And the external nodes are choosing the periphery here, chooses to experiment. And this is an equilibrium because each node in the periphery here has no one to look at. They know that the only person they're connected to is not experimenting. So we assume the costs are not so high that they would themselves prefer to experiment, so they're best responding. Similarly, if we look at the center, then the center is connected to a bunch of people who are experimenting. There's no need for her to experiment by herself. So she's best responding as well. So this is one equilibrium. Unfortunately, even in these very, very simple, the simplest example that I could think of, there are multiple predictions. Because if you look at this situation, this is an equilibrium as well. So this is a situation where the central node is choosing to experiment and everyone else isn't. And this is again an equilibrium because the central node has no one to look at, so she prefers to experiment. She's best responding. And all the periphery, they're very happy because they have someone to look at. There's no need for them to experiment, so they're best responding as well. So these are very different equilibria, and they're different in terms of welfare because if we just summed up utility, this is very inefficient. Here, if there are 5 people who are paying the cost of experimentation, here there's only 1. So this is a much more efficient equilibrium. And also, if you wanted to characterize behavior, there's not much I could say. If you gave me the data that corresponds to it, go figure. So this is kind of a problem. And this was a problem in this literature for a long time. But as it turns out, actually, this is a case in which including incomplete information helps us from a modeling perspective and from an empirical perspective. So suppose we don't know the structure, and let's assume that what we know is that there is actually an Erdős-Renyi or a Poisson network that underlies the formation of these networks. So suppose there is a probability P of a link between any 2 agents. Okay? And everything is symmetric. And so the probability that a neighbor experiments is independent of one's own degree. So this is what I'm going to assume for now. So this means that essentially in equilibrium, roughly speaking, hand waving, the higher my degree is, the less willing I am to experiment. Right? You'd expect that in equilibrium, if everything is symmetric, then higher degrees are more likely to have someone in their neighborhood that experiments. So they would be less willing to experiment. So there's going to be sort of a threshold equilibrium. That's what we would expect. I'm still not being very formal here. But just intuitively, we would expect a threshold equilibrium. We would expect a threshold degree such that if you're a degree that's below that threshold, you would invest in experimentation because you just can't rely on one of your neighbors experimenting. But if you have a high degree, if you have lots of friends, you're going to assume that someone is going to experiment. So it's not worth it for you to experiment. So this is going to be the structure of the equilibrium. And it's going to have very nice, what we call comparative statics. As we change the parameters of the network, we're going to be able to say a lot of things. So for example, if P equals to 0, this corresponds to a situation where no one is connected to anyone, so everyone is an isolated node. In this case, everyone experiments. If P equals to 1, everyone is connected to everyone. We're going to have only one person choosing 1, or if it's a mixed equilibrium here, we're going to have everyone choosing 1 with a very, very small probability. So essentially, we're going to have something that's monotonic in P. So the more connected is the network, the less individuals we're going to expect having experiments. Okay? So this incomplete information helps us get a lot of insights into the structure of the equilibrium. Suddenly, there's a nice structure here. Okay? And this is Caltech complaining. And so the general messages out of this silly example is that first of all, information matters. Second of all, location matters. So we have monotonicity with respect to degrees regarding both the behavior and the expected benefits. Because if you have a higher degree here, then you're able to benefit more from other people experimenting and your payoff will be higher. Okay, so now we'll be able to connect both behavior and payoffs to your degree, which is sort of nice. And the network structure matters. So as we change the network, and in this particular silly example, it was just changing the parameter p, so changing how dense the network is, affects behavior monotonically. So the more links we had here, as we increased p, the less we saw contribution to these experimentations. Increasing heterogeneity has regular impacts as well, and this will be sort of soon in focus. Okay? So this is just to introduce you why looking at incomplete information may help, and this is, and soon I'll kind of give you a more general model accounting for that. The main challenge in all these models is first of all, the complexity of networks, because this example was just for a very silly example of the Poisson networks that I started out by telling you don't fit real networks. So you may ask, who cares? One challenge is to think about a much more general set of networks. The other thing is that we want to a tractable way to study behavior outside of this simple example. So we want to think about different types of payoffs. This was a very, very particular and silly payoff structure. It might be relevant for grains, but certainly there are many other contexts in which the games are much more complicated. So the types of things that we'll focus on are kind of three things. So I'll basically try to give you a model and then think about how these three dimensions affect the outcomes. So first of all, it's the degree distribution. So we'll think about different degree distributions. And in particular, we'll want to know how connected the network is in terms of the average degrees, or for those of you who know what first order stochastic dominance shifts in terms of that. Otherwise, this is just a stochastic way to increase degrees, and I'll spell it out later, so don't worry about it. And how links are distributed across agents. So far I kind of talked about only the density, but later on I'll also want to talk about the heterogeneity of it. So how heterogeneous links are. So it doesn't matter whether everyone is centered around degree of 4, or half of the population is degree 0 and half of the population is degree 8. So sort of the variance of degrees. Yeah.
So this is all going to be sort of randomly chosen links, or
yes.
You're not worried about how connected the left is to the right?
The left is to the right.
Another way to generate identical degree distributions, you could have two graphs, a completely disconnected left side and a disconnected right side. That won't happen if you do it at random, but otherwise you should be worried about this.
Right. So one important assumption that we'll have throughout is that the degrees of neighbors are uncorrelated. So in a way, which I think is linked to your question, because in a way, what you're suggesting is that there are sort of two segmented groups, and if I'm in one group, I'm not connected to you if you're in the other group, right? And this might affect my degree distribution. So this would essentially impose a correlation between the linkages that I am exposed to and the linkages that you're exposed to. We'll assume that they're completely independent throughout the network, but that's a harsh assumption. Now, of course, you could repeat the same analysis for the different subnetworks that are within them, but that's a cheap answer. Yeah. But you're right, we're going to assume independence for now. Yeah. And there are ways to relax it a little bit. I'm not sure I'll talk about it, but we can talk about it afterwards. Okay. So what do we analyze? We analyze a network that describes who neighbors are, whose actions a player cares about, and so on. So this is going to be the general thing. And what I'm going to focus on, and for these talks, is still somewhat simple games, where the actions are in 0, 1. And I'll see how far I go in the next 15 minutes and determine whether I expand this tomorrow or not. But for now, we're going to focus on binary games. You'll have to have faith that things expand also to more complicated games. So we want to examine equilibria and know how play diffuses through the network. Okay, so let's go back to our notation just to make just a reminder. Gij is this adjacency networks that correspond to whether I and j are connected or not. Nij is the neighborhood. Di of g is i's degree, and each player chooses an action in 0, 1. Okay, so I went through this quickly because we saw you saw this before, but stop me if I'm not clear. Okay, so payoff depend only on the number of neighbors choosing 0 or 1. And for today, for now, for the next 15 minutes, we're going to think only about complements. So you'll see what I mean by that. We're going to normalize the payoff of all neighbors choosing 0 to 0. So if everyone is choosing around me 0, I'm going to assume that my payoff is going to be 0. But VDX minus CI is the payoff from choosing 1 if the degree is D and a fraction of X of neighbors chooses 1. Now, importantly, and this is where the complementarities come to play, we're going to assume it's increasing in X. I may or may not tell you what happens when it's decreasing in X tomorrow. It depends on time. So we're going to assume that the more other agents are going to choose the action 1, the more of a benefit I myself get from choosing the action 1. You may want to really complain now because it doesn't match the example I just gave you. So I wanted to choose a very, very simple example to illustrate the forces of information, but this is kind of not the best of styles because it doesn't fit this setting. I hope you'll forgive me. CI is this cost of choosing the action 1, and we're going to assume that it's distributed according to some distribution. Okay? In particular, it could be a fixed cost, but for most of the time, I'll just assume it's distributed according to some distribution H. Okay, so different people may have different costs of choosing the action H. So here are some examples of what this sort of setting might capture. So you can think about a dependence on average action. So this is just like the classical coordination games for those of you who are economists. Or a choice of technology where you really care about the average number of people, for example, who switch to a Mac or switch to LaTeX or whatever. And in this case, you might really care about the average number of people in your neighborhood who've switched over or who learned a new language. And you may have these costs, by the way, and these examples really have a meaning because some people have a much easier time learning a new language than others. The total number is, again, an example that is relevant for many applications. So this may, again, be a situation that matches learning a new language. You may need partners to use a new good technology. So this is just like me working with co-authors, and I really care about the number of co-authors that actually uses a particular software because we'll have to share files, and so on and so forth. You could also think about something that's less continuous. So a situation where this value of choosing the action 1 is 0 up to some number, and then it becomes 1. And this is a model that actually appears in the literature and political economy because it sort of corresponds to the way revolutions happen. So sort of you want to revolt, but your revolting is effective only if there is enough people standing in a square and screaming. So this corresponds to this sort of model which is captured by our setting. You could also think about a V that is declining in D. Yeah?
You may have said it, but what's the utility of selecting 0? Is that
It's
zero?
normalized to 0. So we're just assuming, yeah. We can get back to it later. It doesn't matter much
If
other
I
than...
select 0, then I don't care what other people say.
Exactly.
If I select 0, it doesn't matter what my neighbors say?
Exactly. Yeah, so you always get 0. Yeah, and if you select 1, then it depends on your neighbors. Okay. Okay, so this is just a normalization. So if I stay at home, I always get 0. If I go to the square and revolt, it depends on how many others are revolting.
But if I stay at home and everyone else revolts, it's pretty good for me.
Not in this model, because I don't get a kick out of contributing to the revolution. Okay, so VD, and this is something that could be relaxed. I mean, you raise good points. It's not that I think this is always the case. For now, it's sort of a normalization because we could always add, so for the analysis of behavior, it doesn't really matter. We could always sort of add stuff to the utility itself in an appropriate way. When we start thinking about welfare, for those of you who are economists, so when we start summing up utilities, it may actually matter a little bit, and I'll try to remember to mention that. But for now, it's a normalization. I'm just using it to give you a simple model that captures a bunch of things, and that's it. Okay, so the last example that is captured here is V, which is declining in D. So you can think about information aggregation. So suppose that what we're doing is just kind of sharing our information. There's a marginally decreasing effect of degrees, effectively. Okay, so I described to you the networks and the payoffs, and now we're going to think about information. Okay? So I'm going to think about incomplete information, which means that you know only your own degree and assume that other types are governed by the degree distribution. Okay? So this is really just like incomplete information games where your private type is your degree. That's the only information you have. We're going to assume no correlation in degrees. That's actually sort of an iffy assumption. So just to be completely honest here, this not only relates to the point that Eva raised about certain applications in which you'll have sets of people that are connected to one another in separate ways. So I'm not connected to many people in Milwaukee, for example, just because I live far away. But in addition to that, the no correlation assumes kind of in the background that we're looking at very large networks. And the reason is if you have a very small network, degrees are going to be correlated. So think about a network that has 2 nodes in it. If one of the nodes has degree 1, it must be the case that the other nodes has degree 1 as well, right? So the degrees are highly correlated, right? Essentially, they have to be the same. This is the case, in fact, whenever you have a finite network. So we're going to assume no correlations. You can actually relax that a little bit or think about a very large network. There are different ways to go around that, but that's going to be the assumptions to illustrate results to you. And we're going to think about Bayesian equilibria. How many of you have seen Bayesian equilibria? It occurs to me that... Okay, we're all good. So this is a situation where, given your information, you can actually update your beliefs about other people's types, and then you best respond. Okay, so it's kind of a natural extension of Nash equilibrium to a case of incomplete information. Yeah?
Does the vacuum distribution depend on my type? So if I have a larger number of people, do I'm connected with waiting something else from the distribution?
No, the distribution is determined ex ante, and that's set in stone. And that's exactly, and we use it to determine the network. But once you see your own degree, you might deduce something about the realized network. Right? For example, you might deduce something about your neighbor's degrees. Now, the other polar extreme is complete information, where you know the network that has been realized. So this just corresponds to the case that gave us a lot of trouble, even in this simple experimentation game with multiple equilibria. And here, kind of the natural concept to have in mind is Nash equilibrium, because there's complete information. So these are kind of the 2 types of information settings that I'll try to contrast. You can think about intermediate stuff. I won't talk about it, because you can think about situations where you know not only your own degrees, but the degrees of your friends. So I have fairly good information, I think, about my close friends. And so on. So you could think about kind of the radius of information that you have, and there are some interesting extensions to do that. Okay, so let's think about the incomplete information case in the next 5 minutes. And I'll just start kind of sketching what happens in this model, and we'll continue tomorrow. Okay, so G is drawn from some set of networks such that several things happen. First of all, the degrees of neighbors are independent, like I said. So this is this harsh assumption. And the probability of any node having degree D is P of D. This is just like we did in the beginning of today's talk. Now the probability of a given neighbor having degree D is given by this thing. Now this is sort of important because a surprising number of papers actually mess that up in the literature. So if you think about the degree distribution of my neighbor, even though the degrees are not correlated, the distribution is not the same as the underlying distribution. Why is that? Let's think through a very, very simple example. So suppose that the population, our fig population, was composed of half agents of degree 1 and half of the agents of degree 2. Now let's think of a random agent, but let's say this is me, and I have one link coming out of me, one arm that I can shake with someone in the population. Now if I randomly link it to someone, to some arm in the population, the probability that I hit an arm that belongs to a 2 agent is higher than the probability that I hit an arm of a 1 agent, right? They're essentially 2 times the double of these arms, right? So in fact, the probability that I hit an agent of degree 2 is 2/3. It's not 1/2. So we need to normalize essentially this distribution by the degrees of these agents. So this is where this formula of D times P of D comes into play. Okay? All right. So the type of agent I, and this may probably speak more to the economists in the room who suffered through this in their first year, is just the degree of agent I and their cost. Okay? So essentially when we think about the Bayesian equilibrium, this is going to be your private type or your private information. Given this type, you're going to update and best respond. Okay? So the strategy space are these mappings from the set of types, these degrees on costs and realized costs, to whether you're going to choose the action 0 or 1, potentially mixing. Okay, so this is why this delta. Okay, so now I'm gonna write down the fixed point equation, and then I'll end so that we can start afresh tomorrow and analyze this. Okay, so let's denote by h of v dx the percent of degree D types adopting action 1 if x is a fraction of random neighbors of adopting. I wish I had a board here. So recall what when do you adopt? Choose 1 if v dx minus c is greater or equal than 0, because this is the value from choosing 0, this is the value from choosing 1, so this is when. Oh, choose 1 if v dx minus c is greater than equal to 0. Is that everyone can see? Okay. Because 0 is what you get if you choose 0, and this is what you get if you choose c. Right? So basically, when you're a degree D agent and you think x is the fraction of neighbors who choose the action 1, you're going to choose 1 if and only if c is less than or equal than v of dx. Right? Now, what's the probability of that? We know that C is determined according to the distribution H, right? So the probability that C is less than this thing, the probability that C is less than V of dx, is just the cumulative of V of dx, right? So this is the probability that the agent of degree D has a sufficiently low cost that they're willing to choose the action 1. Okay? So this is where this is coming from. Does this make sense? Okay, so this is the basic building block of our fixed point equation. So h v dx is the percent of degree D types adopting action 1 if x is a fraction of the random neighbors who are adopting. Okay, so how do we calculate x? Well, x is the fraction of neighbors who are adopting, right? So this is all the probability that my neighbor is of degree D, okay, times the probability that the degree D agent adopts, right, or chooses the action 1. This is this H monster. Right? But the probability that my neighbors is of degree D, we just said it's not really the underlying distribution. It's this thing that depends on the underlying distribution and the expectation. This is this D times P of D over P of D. Right? So these elements are just the elements that corresponds to the degree distribution of my neighbors. So this is just the probability that a random neighbor of mine is of degree D. And then this is the probability that conditional on them being of degree D, they actually choose the action 1. So now I took the expectation over this, and this should equal x. So this is really what captures the equilibrium in this network. So this is going to correspond to our steady state or our equilibrium of this network. And what I'll do tomorrow is kind of start out with this equation. I'll remind you of stuff. And use it also to think about some simple dynamics. So that's all, folks, for today.